If you point a laser pointer at the moon, you don't get such a tiny dot. You get a spot the size of a city. And not because your laser is cheap as mine. Not because the air ruins everything. Even nearly perfect laser beam cannot stay parallel forever. And that sounds impossible, because the laser beam starts out in the cavity as a straight, perfectly straight. What makes it spread? The photons in the beam don't feel each other, they cannot repel. And the answer is not in bad engineering, the answer is in physics. A laser looks like the most straight thing in the universe, but more carefully you look at, more opposite it reveals. We usually draw light as rays. Straight lines, clean arrows, perfect geometry, and it works beautifully until it doesn't. A real light has a width, probably millimeters, probably centimeters, probably a meter if you expand it through a telescope. And that changes everything. As long as light is finite, it has kinda edge. The edge limits its size in space. And that fact changes everything, because limited in space beam cannot keep only one direction. And that's a core of a problem. A really parallel beam has to be infinite sideways, not simply wide, infinite. A real beam is never infinite, so it cannot be perfectly parallel. Wait, did I hear right? Quantum uncertainty impacts a laser pointer, right? Let me explain how this divergence works mathematically. The light going upwards has only one component of momentum. But if it passes through an aperture, everything changes. Now we know where in x direction the light is localized. The light is actually quantum object, therefore we have uncertainty principle. And if we know x, and if x is somehow certain, it makes momentum also somehow certain. And that immediately creates value for x component. It was 0 and now it's not 0 anymore. Therefore, if light passes through an aperture, its x component is not 0 anymore. So it starts to go aside as well. How much does it actually spread? What does math say? Please like this video, because I really need your support. Consider subscription. And your question in the comment will be really helpful to development of the channel. How much does it actually spread? The simplest way to think about is this. The divergence depends mostly on the ratio of the wavelengths of the light divided by size of the aperture, or beam diameter. Make the aperture bigger and the beam spreads less. Make the wavelength shorter and the beam spreads less. For the circular aperture, the diffraction limit is written this way. Here again lambda is wavelength, d is diameter of the beam, and 122 is result of some math. Just trust me, I am a doctor. And if the formula feels familiar, it's not a coincidence. Actually, the physics which does not allow us to see distant stars and the physics which does not allow beam to stay narrow is the same. And that's not a wondering fact, it's optics. Let's take an ordinary laser pointer. I guess this one is ordinary enough. And the beam size at the exit is about 3 mm. The wavelength of the light is about 650 nanometers. Let's make some math. The wavelength is tiny. The ratio of the wavelength and the beam diameter is also tiny. Only a few thousandths of degree, it's almost nothing. But the moon is far away. It's actually almost 400,000 kilometers. And over that distance, even a tiny angle makes the beam enormously huge. By the time the dot reaches the moon, it becomes a spot of 100 kilometers. 100 kilometers in diameter. It's enormously huge. That's 3 times bigger than the narrow part of La Manche. And now the question becomes more strange. There are reflectors on the moon of that size, not 100 kilometers. What the hell? Apollo astronauts, Soviet rovers, and many other missions left reflectors on the moon. They are not regular mirrors, they are retro-reflectors, so they are specially designed cube corner mirrors. And if a light enters that cube, it reflects exactly backwards. But they are not kilometer size wide, they are even not hundreds of meters. The regular size is roughly half of the meter, and the smallest is of 5 centimeters. I don't understand what did they expect. But there is surely a reasonable answer. The beam doesn't spread because it hits the edge. The effect is not related to any interaction with the aperture. The only confinement is important. The photon does not bounce off the edge. It spreads because of narrow wave cannot contain only one direction. This laser gives a spot on the moon of at least 100 kilometers. That's too much, that's not about any application. And how can we drop this value? And the answer is easy, because the size of the spot on the moon depends only on divergence. And divergence is limited by this value. If I make this beam twice bigger, not 3 but 6 mm, the spot on the moon will be not 100 but 50 kilometers. So density of power will be 4 times higher. Secondary, we can drop a wavelength. Let's say not 600 but 500 nanometers. Moreover, green lasers are well developed and they have high power. So we got the direction, we have to make the beam wider. 3 mm gives 100 km on the moon, 6 mm 50 km on the moon. What if we make the beam 100 km? First of all, it's technically complicated, and secondary, it will not give us 3 mm on the moon. The beam will remain 100 km. But the divergence will be, I guess, about 3 mm. Especially for you, I did some math how size of the spot on the moon depends on the initial beam's diameter. When the beam is too small, it expands because of diffraction. When the beam is too huge, it remains huge. Which size should the beam be to have the minimal spot on the moon? My math says if the beam diameter is 17 meters, spot on the moon will be of 24. Actually not too bad. Those 25 meters are theoretical limit. It can never be reached, because at least the atmosphere distorts everything. That was my prediction. How does the real experiment looks like? And what's a real beam diameter? The real lunar laser ranging Apache Point Observatory. First of all, they use something more serious than my laser pointer. A fancy laser, which is passed through a huge telescope. It's not only a receiver, it's also a transmitter, so they use it to expand the beam to the telescope aperture, which is huge. It changes whole game, because then the beam is expand, and that allows to drop the divergence from 100 kilometers to 100 meters. That means the reflectors reflect 1,000,000 times more. At the Apache Point Observatory, they use green laser, which has smaller wavelengths compared to red one, so divergence is less. How to understand then what time is needed for the light to travel to the moon and come back? For this they use not a simple laser, they use a pulsed laser. We clearly see when pulse has departed, and then we simply have to catch a moment when light came back. We know when pulse was sent, we know the time when pulse came back, and from the delay between them we can measure distance to the moon with a precision of a few centimeters, sometimes even better. The process itself is really ineffective. We illuminate on the moon a spot size of 100 meters, and our reflector is 45 cm in size. And since its size is limited, we are getting divergence again, which is even stronger than we have had before, roughly 10 times stronger. And to compensate such crazy loss, the pulse is incredibly powerful. Each pulse contains that much photons. 17 zeros. So we are sending one spreading wave, and then the reflector catches a tiny part and sends back another spreading wave. And modern technologies allow to detect even a single photon. So if we are getting a bunch of them, let's say 100, we are already happy. So the telescope is not catching a bright flash, but just a few photons are already enough. If you are interested how to detect a single photon, I am happy to explain. I was working with the technology for several years. I have even had a lab course about. Who has left a reflector of 5 centimeters on the moon? They are not idiots, they simply did not purpose it to be shined from the Earth. As far as I understand, if you are flying around moon, at some moment you need to check your position. And if you're already quite close, the divergence doesn't play such a big role. So engineers are not idiots. Please like this video, cause I really need your support. Consider subscription. Thank you for watching and see you in the next videos.